Welcome back to Beyond the Patterns. Today I have the great pleasure to announce another invited talk, and we have invited Udaranga Wickramasinghe from EPFL Lausanne, Switzerland, and he will present on his latest work that he also published on MICAI Conference 2020. So he is a PhD student at CV Lab EPFL and is advised by Professor Pascal Hua. His research focuses on 3D surface extraction from volumetric images and ways to introduce prior knowledge into deep neural networks. Prior to joining the CV Lab, he completed his master thesis in computer science at EPFL and in his bachelor's degree in 2014 in electronics and telecommunication engineering at the University of Moratuwa, Sri Lanka. So it's a great pleasure to announce him here as a speaker, and the presentation will be entitled Voxel2Mesh 3D Mesh Model Generation from Volumetric Data. Udaranga, it's a great pleasure to have you here, and the stage is yours.
Hello, everyone. Thank you very much, Andres, for the invitation. It's really a pleasure to talk to you all about my work on Voxel2Mesh. So the work I did, the work I presented during last MICAI conference was on the idea was Voxel2Mesh. It's about 3D mesh model generation from volumetric data. So before directly moving on to our architecture, let's little bit talk about an overview about shape representation in general. So there are two main categories that we use to represent shape in computer vision or computer graphics. One is the volumetric representation side, and the other is the surface representation. At the moment, the most popular way to represent shape is actually the volumetric representation. So a few of the ways, techniques that fall under volumetric representation is occupancy grids, sign distance fields, or octrees. So here I have shown an image of a lever extracted from a CT image, a CT scan. And in voxel in volumetric representation, which is represented using an occupancy grid. So occupancy grid basically is a 3D tensor that has 1 if there is an object and 0 if it does not have the object of interest. Similarly, then we have a sign distant field. It is a slight extension of the occupancy grid. Instead of the occupancy, an element or a voxel in this grid will have the distance to the surface. Octree is not that common still in computer vision literature. There are about maybe handful of papers in the literature trying to develop deep learning techniques with octree, but it's a more memory efficient way of representing 3D objects in 3D objects. So all these things falls under volumetric representation. Then we have the other part, which is this surface representation, which was my interest. So in surface representation, instead of representing the volume, we are representing the surface of the object. So this surface representation, the most common way of representing surface is using meshes, which is a collection of vertices and faces. And also you can say point clouds also fall under surface representation, but I put it under brackets because within brackets, because it does not necessarily have the surface information or the face information as in a mesh, but still it has the points on the surface. So these are the all types of ways, or more common types of ways representing or objects or shapes in 3D. Now, if we look at the current literature, there is no argument that the volumetric representation is dominating the field. Like in 2016, UNET paper came out, and along with all these segmentation papers, that they use occupancy grid to represent the object at the output, and 99.9% of the papers are using volumetric representation. And also more recently, going beyond the occupancy grid, there are deep learning based approaches that use sign distance fields to represent objects. It is still not yet seen in the medical imaging community yet, but in the for shape modeling, especially people working with the ShapeNet datasets, there are very interesting papers that use sign distance field to model shapes. And so, but all these things fall under this volumetric surface representation, volumetric shape representation category. But now the interesting thing is, if you talk to someone doing research with in life science sections that who analyze organs or medical images, or someone doing clinical practices, there are a lot of people that are interested in measures. One reason for that is that they want to analyze shape of structures. They want to compute statistics based on area-based statistics, or how the shapes are changing between subjects, and so and so. And also for visualization purposes, there is advantage of using. I mean, we use measures for visualization. It's the rendering systems and all. They work much better with measures. So there is always a preference for. Not a preference, but there are a large group of people who would like to have measures, to extract measures from input images. So at the moment, the pipeline they use is, they would start with the input volume. They would train a unit, a CNN, a unit, or some variation of a unit, or a more advanced version, and get a prediction from this. So when you train the unit, you will have this input image and ground truth pair collection, a data set. And then when it predicts it, you will get something like this, a prediction. So this is again an image of a liver that this taken from this CT scan. So if you have trained a unit, one thing for sure that you have noticed is that you get at least one or two small false positive regions that appear around at least some of the predictions. So the first step in generating the nice mesh is that you need to get rid of these things. You remove this false positive region. And then we run a marching cube algorithm, or there are some other algorithms as well that people use, but most commonly it's a marching cube algorithm that you use to convert this volumetric representation, this occupancy grid representation, into a mesh. But even like once you obtain the mesh, what you notice is that it is corrupted by the pixel noise or voxel noise. What I mean by is that it's a discrete grid, and this discrete grid results in non-smooth surface when you obtain the surface mesh. So you will add a little bit of mesh smoothing, because the organs are most of the time smooth. They are not as discontinuous, or you don't have the noise that you see when you run marching cube on the output of a unit. So when you do the mesh smoothing as well, you will obtain a nice mesh. Not perfect, but still you would obtain the output mesh like this. So with Voxel2Mesh, what we propose is there a way that we can go from input volume to output mesh and get rid of this all post-processing stuff and have an end-to-end trainable architecture? So that was the motivation. Is there a way that we can do this? And if we can do this, we can build more and more complex systems that which are end-to-end trainable. So here we present the idea. So what would happen is, like, we are replacing, we take input volume, we have Voxel2Mesh, which outputs the mesh. So here is a result from Voxel2Mesh architecture. So now I come to the inspiration that I for this architecture. So when we first had this idea, I was looking in the literature, has people tried something similar? In the early 90s, people had the idea of deformable models, snakes in 2D and also 3D deformable models. So the idea was, you start with a mesh, you deform it to match underlying object. So this idea was there in the 1990s, but it has died out ever since. After 2000, it was not that popular in the literature. But when I was going through the recent literature, I came across this paper, which was called Voxel2Mesh. So this is a subgroup of people who work on the problem trying to predict 3D measures from 2D images. So it has similarities, but it's slightly different. So the 2D image is a photograph of some object. So it has lost some information because you project the 3D world to the camera sensor. So from this input image, you want to imagine the 3D image, 3D object. So Voxel2Mesh was addressing this issue, and the architecture is inspired by this approximately by this deformable model ideas, because it is starting with a sphere mesh and it is deforming this gradually. So it demonstrated that we can use graph convolution to deform an object to predict a 3D shape using an input image. But the thing with this is that here their focus is more on a task of extrapolation. The 2D image has less information. You need to imagine things to predict the 3D image. So they have very deep graph convolution layers. They have many graph convolution layers, and the way they use simple technique to exchange information between the voxel and the mesh decoders. And the focus has been mainly on this extrapolation idea. How can we imagine a 3D object from a 2D image? In our case, that the objectives are slightly different. We have the 3D volume at hand. We have a 3D image. It could be a CT image, MRI image, and we want to fit the let's say a circular mesh as good as possible to the exact surface boundaries of the target object. So we propose some updates how we can adapt this architecture to our task of extracting 3D surfaces from 3D image volumes. So mainly what we did was we added a a decoder part, a voxel decoder, which was not present in the Voxel2Mesh architecture. And we improved how we sample features from the voxel features. And also we improved upon how we subdivide meshes. So before explaining this in detail, I will just give you an overview of the architecture. So we start with input volume. The top part of the architecture is a unit. There is no difference from this voxel encoder and voxel decoder and a unit. So the novelty is at the bottom. So what we do is we have a unit at the top, and we have a set of graph convolution layers. We can say like that. We have a set of graph convolution layers at the bottom that exchange information between graph convolution layers and the voxel features. Simple as that. And the graph convolution layers, it takes a circular mesh as input. It extracts features from this voxel features. It deforms this mesh gradually, step by step, such that it fits the target. So we have the so you have a mesh deform layer and adaptive unpooling layer. So a more accurate term for this would be mesh subdivision, but since in this modern literature is unpooling is more popular, we use that term as well. So mesh unpooling is actually mesh subdivision. So the key reason we need this unpooling is that we want to start with a simple mesh. What do I mean by a simple mesh? Is a mesh with small number of vertices and gradually increase the number of vertices. If we start with a mesh with the full vertex, with a very high number of vertices, it will be consuming too much memory, and that will increase training time and also affect it will reduce the size of the models we can train. So what we do is initially we start with a simpler mesh which has lower number of vertices. In our case, we either chose 162 vertices or 642 vertices, depending on the experiment. And in the first layer, what you do is you take information from the voxel features and we use it to deform this sphere a little bit. After you deform it, we introduce new set of vertices, which I will explain in detail later. Which we we end up with this intermediate liver image, and then we repeat. So when we repeat it, now we are extracting information from a different stage in the voxel decoder. So this stage has slightly higher resolution compared to the previous stage. So that means it can make much finer adjustment to the vertex positions than in this situation. So again, we repeat it and we repeat this cycle and we come here until we come here. So at each stage, we are making finer and finer refinement because we are extracting information from high resolution features. And also we are also introducing new vertices along the line so that it has enough vertices to fit this high resolution information that's coming from these high resolution feature vectors. Another thing is that now on UNet, we only have the cross entropy loss at the end of voxel decoder. Similarly, we also have the cross entropy loss at the end of the voxel decoder. But with the mesh decoder, we use losses, the chamfer loss and a subset of regularization losses, which I will describe later. But they appear here as well as at the end of each stage. So this actually speeds up the training a little bit. So that's why we went up. Even if you don't use at the end of each stage, it's fine. It's just the training is a little bit slower. Okay, Now that's like the very basic overview of the idea we worked on. And now let me go into more details. So this mesh decoder. In the mesh decoder, we have the mesh deformation that does, which does this vertex update. So how does this vertex update happen? Let's say you are at stage L-1. If I go back, we have 3 stages. So I'm saying, so we are L-1. So each vertex in the mesh has an associated feature vector. So what do I mean by this is that we have computed search, we assign certain features to each vertex. So how do we do that? So the easiest one is this feature is the coordinate of the vertex. So it's a feature associated with this vertex. Then we have XL. This XL is the feature extracted from the voxel decoder, and at the corresponding to this specific vertex. So this XL is extracted from the voxel decoder and is correspond to this vertex. So how it correspond, I will explain later in the how we do this sampling operation. But for the moment, let's say this XL is the feature that we extracted from the voxel decoder. VL is the coordinate, and which then we are left with ZL-1. So this ZL is a latent feature vector that is a result of output of the HL function we have defined from the previous stage. So when we input FL-1 to HL, it output ZL. So this ZL goes as this latent vector goes to the becomes a part of FL, the feature vector associated with this vertex. So once you have this latent feature vector, we use this feature vector to predict the deformation for the vertex. So this coordinate XYZ coordinate is given by VL-1. We want to shift it. We want to shift it a little bit. And this is given by the second function delta ZL. So we tried out several versions, like instead of finding the delta, why just directly predict the vertex? We found out it's much easy, more accurate when you predict the difference instead of trying to directly predict VL. So it's what I mean is that without predicting VL minus, delta has to directly predict VL. So that was less efficient, less accurate. So we realized that if you only predict the deformation, the delta, it's much efficient, more accurate in the predictions. So these are the two functions we have, and both of these functions are approximated by a set of graph convolution layers. So each HL consists of a graph convolution layer with four graph convolutions, and delta L is also similar. So that is the basic idea how we compute a deformation for a vertex. So this deformation is computed for all the vertices, and that's how vertices slowly, nicely move to fit the target. Once we have this, now we need to see, okay, I talked about graph convolution. What is the graph convolution, or I call here mesh convolution that we use? There is plenty of room to improve here. We use the basic one. The idea is here the feature vector F is this feature vector, or this general feature vector F associated with the vertex. So we have a weight vector that associated with F, and also this is the set of neighbors of for a given vertex. So each vertex will have a set of neighbors around it. So these neighbors are, this NV is the set of neighbors of V, and we have this second term that accumulate information from the neighborhood. So this accumulation information from the neighborhood of vertices is important, like it's very important. If you get rid of this term, Voxel2Mesh does not work. So in my experience, maybe you can define much different convolution and get it working, but so far my experience has been this second term has been crucial. You need to get information from the neighborhood. You need to have this term. And so basically you have one weight vector that determines the contribution from the feature vector associated with the vertex. And then you have the other feature weight matrix that determine the contribution from the name. So there is this other term, this thing. This is basically that when you deform, you can have some vertices far away from a vertex and some vertices very close to the vertex. The basic idea is if a vertex is close to another, the center vertex, this should have more influence on this vertex than a vertex which is far away. So we have this a coefficient, normalizing coefficient that assign a weight based on the distance. If it is too far away, that even though it's a neighbor, one ring neighbor, its effect is less because it's a far away vertex. But if it's a close vertex, it has more effect on this on this vertex. So this term determines this the weight, and this is a constant that determines how which is considered far away and which is considered closer. So this is the mesh convolution or graph convolution we are using. So that is like, okay, this is this sums of this mesh convolution, and the mesh vertex update sums of the mesh deformation part of the mesh decoder. Now we move on to the adaptive unpooling. First learn neighborhood sampling, next adaptive unpooling. So what do I mean by learn neighborhood sampling? Before I say what's learn neighborhood sampling, I have to first define what is sampling. So this terminology is taken from Pixel2Mesh work as well. So sampling is basically, we want to exchange information between the two representations. We have the voxel feature map here, and then we have the mesh. We need a mechanism to exchange information between these two representations. So the idea is you have a vertex given by its x, y, z coordinates. We go to the corresponding location inside the voxel feature map. Now the thing is, this coordinate is a continuous value, but the voxel feature map indices are discrete. It's on a discrete grid. Now, how do you find a feature associated with this coordinate in a discrete grid? The technique is that we use in 3D bicubic interpolation technique. So if the vertex is close to a one voxel in the feature map, that feature vector inside that voxel will contribute more, and the voxel that is far away from the vertex will contribute less, but it will have some contribution. So this the sampling refers to the idea of by performing interpolation using the voxel vertex positions. So once you do this type of sampling, so what it will do, so it will extract information at the location of the coordinate. But now the thing is, we are interested in finding the distance or the deformation to move from this point to the boundary of the target object. So what we found out was, like, instead of just sampling at the center, like they do it in the Voxel2Mesh paper, we should also sample around it neighborhood as well, which gives more information about the direction that this delta that we need to learn to move this voxel, move this vertex in the space. So we would sample at the vertex coordinate plus a set of neighborhood, a set of neighboring points. So how do you find these neighboring points? We learn it as well. So we have auxiliary small network. Given a point and the features associated, it predicts where to sample. So with that, we take the central location and we sample another set of features from the neighborhood. So all these features together is passed to a auxiliary network function, we can call it function G, that produce this Excel feature vector. So by doing so, we gather more information, the network can more accurately predict how far it has to move and in which direction, more importantly, it has to move the vertex towards the boundary of the object. So this the learned neighborhood is what I mean by learned neighborhood, is that we are learning the neighborhood we need to sample. So we have the center point and the neighborhood that we are sampling. So this is how we extract information from the voxel feature map and move them to the mesh features, to the mesh. So now we discussed about mesh deformation and the sampling. So what we are left with is adaptive mesh unpooling or mesh subdivision. The subdivision idea, the main reason that we worked on this was like GPU memory constraint, because to have better accuracy, you need more vertices, but when we start increasing vertex, GPU runs out of memory. Adaptive mesh unpooling is a strategy that we developed to address this issue, but still it's not fully solving. There is so much room for improvement. So, but let me explain it briefly. So let's say we have this mesh at stage L-1. You have a set of vertices. As the first step in adaptive mesh unpooling, we introduce set of candidate vertices. How do we come up with candidate vertices? We come up with candidate vertices using uniform unpooling. So this is the uniform mesh subdivision is the strategy that everyone uses in Voxel2Mesh and all the variants that was developed after Voxel2Mesh, almost all. There is also, so here what we do is we take an edge, we split it at the center. Take an edge, split it at the center, and we can define new. So this large single face become 4 small faces. It's simple as that. It's not a complex technique. So, but we don't stop there. We call this only candidate vertices. Now with this one, we deform this mesh to see which vertices move and which vertices does not move. So what's the intuition? So basic idea is, if you take a structure, some part of the structure might be flat and some part of the structure might be very curvy. So the curvy regions will need a lot of vertices to explain its geometry, while the flatter parts does not need much vertices. So what happens when we introduce vertices uniformly throughout the mesh and then deform. In the flat regions, the new vertices does not move too much from its original position because it's already flat. It does not need more vertices. I mean, it's already flat. It does not have to move a lot to define the geometry. But if it's a curvy region, the new vertices will move because it's more, it has more high frequency information. It has to capture this information. The vertices will move. So these are the ones that I've shown in green arrows. The red arrows, okay, these are the regions that correspond with the more flatter region. Now, what we do is that we drop these vertices that did not move too much. From this, we can decide, okay, we remove the 20% or 80%, no, let's say 30% of the vertices that has the least movement. Likewise, we can artificially or manually control the number of vertices that get added at each mesh subdivision. And the ones we remove are the least informative ones, not the most informative ones. So we get to keep most of the accuracy and get rid of a lot of vertices that does not add much value. But removing vertices breaks the phase information. So that's a big issue. If you drops a lot of vertices from a mesh, the phase information is not valid anymore. We have to remesh. So that is a very tricky thing to do. But luckily, if I go back to the Voxel2Mesh architecture, we are starting with a sphere. What we are learning with Voxel2Mesh is a mapping from a sphere to a surface. And luckily, we know how to efficiently mesh a convex object. We have convex hull algorithm. We can efficiently mesh points on a convex object anytime. It's a very efficient algorithm and works all the time. The lever can be non-convex. It does not matter. The deformed surface can be non-convex. It does not matter. But since we have this mapping, we have the correspondence between the vertices in the sphere and the final mesh, we can, whenever we subdivide the lever, we would be subdividing the input sphere as well. Whenever we drop vertices from the lever, we are dropping vertices from the input. We can drop these vertices from the corresponding vertices from the input sphere mesh as well. Then we do the remeshing on this sphere mesh, and we transform this phase information from the sphere back to the lever. And we have new phase information. So this is, so with this three steps, we can adaptively control the amount of vertices and get so that we don't run out of GPU memory and still get accurate meshes. So these are the three modules, in the main three modules in the Voxel2Mesh architecture. Now I go to the final bit of detail. Without this, it's not complete, the loss function, but it's same as in Pixel2Mesh architecture. It's nothing new. We have the chamfer loss, normal loss, normal consistent loss, Laplacian loss, edge length loss. But unlike the Pixel2Mesh architecture, we have the cross entropy loss as well, because we have a voxel decoder as well. So these are I'm using the standard definition, nothing new here. It's just for the sake of completeness, I included this slide. So now I move into the results. So to quantitatively analyze this, I use two publicly available datasets, one from this liver dataset and hippocampus, available from some or publicly available. And the synaptic junction dataset, it is a dataset from EPFL. So we compared this with Voxel2Mesh, and in almost all the cases, it was performing better than the baseline methods. So one thing to note here is that I'm using intersection now or union as the metric, but the Voxel2Mesh is outputting a mesh. So how do I do this evaluation? So I have also implemented a Voxel mesh rasterization algorithm, the standard mesh rasterizer in GPU. So I take the mesh, I would rasterize it and take it back to the voxel domain so that I could compute this metric. I would not call it the best way to evaluate Voxel2Mesh, but we have to compete in the battlefield that exists. So I took this extra effort to compute IOU so that we could compare with unit. But the more interesting things come when we look at the qualitative results, not the numbers. I mean, numbers, of course, you have better performance, but how do they come? With UNet, what you notice is like this type of false positive regions, or this type of topology errors. So before that, I will briefly explain the dataset. So the first two are from electron microscopy data. This of a brain of a mouse, and we are trying to segment the synaptic junction, presynaptic neuron and postsynaptic neuron. So this is the synaptic junction, presynaptic neuron, postsynaptic neuron. So this is the ground truth. This is the liver I've shown you many times now. And this is an MRI image dataset and the hippocampus of from the brain. So these are the ground truth. This is UNet. So when you do with UNet, what you can do is we can, of course, remove the post-processing where you remove false positives by running connected component analysis and then matching cube and bit of mesh smoothing. We can come to this. The thing is, you can get rid of parts like this, but the parts like this still prevail. You cannot do anything about it. What we notice with Voxel2Mesh is that it tend to better learn the overall shape. So this was not our initial objective of doing Voxel2Mesh, but this is what we observe once we do it, that once we explicitly model the surface, it tends to learn the surface property, surface shape much better than the voxel representation. I'm not saying it totally eliminate, because if you look at here, there is a small shape anomaly. Yeah, it's there, but compared to the anomalies that UNet makes, it's significantly less. So this is something interesting that we noticed when we that added bonus we had with Voxel2Mesh of training this end-to-end trainable models with having explicit shape modeling shape surfaces. So now, okay, so this was our work for the MICAI 2020, and then there was one paper that came a couple of weeks ago, I think about a month ago, that extended Voxel2Mesh to model hearts of in MRI image. So that was done by a group in Berkeley, and they improved Voxel2Mesh architecture. They introduced better ways to initialize the positions of this the initial spheres, because in the original Voxel2Mesh we have all the spheres initialized as the same position. So they find a clever way to initialize the initial spheres correctly in a better way, and they have defined the final loss as well slightly differently. And the most interesting thing that I saw from this paper was this image, that they compare the worst case behaviors. So this is something very important, that in medical imaging, we want to quantify how our systems would behave. So in that aspect, one thing we need to address is, when things go bad, how bad does it go? So with one thing with UNet is that when things go bad, it goes catastrophically bad. So this is an example, a classic example of this. So we have a 3D unit, and the worst case, you have this hard segmentation. So here, this is Voxel2Mesh with better initialization. They have actually further improved their architecture, and interestingly, it was nice to see, like, they also have the same, like this false positive regions, that floating points, this one pixel here, one here with the unit, and here also this part, this random false positives appearing here and there. And the Voxel2Mesh, because we are explicitly learning the shape, the surface, it better learns to avoid these catastrophic failures. And I think this is one of the strength of Voxel2Mesh, that even at the worst case, we have maybe we'll have to try a little bit more, but so far what we have seen is it's the worst case behavior is better with 3D unit. Of course, to verify, we'll have to see many more papers down the line. Only then we can come to a conclusion. But so far, from my experience, as also from this paper as well, that's what we can see. So then, yeah. So then this is the second extension. This is something we did, which will appear in CVPR 2021. There was one issue with Voxel2Mesh. When we model these neurons, in some instances, when the neurons were touching the boundary of the image, they were deforming badly. So we needed a way to better control the deformations of the vertices. And for this, what we did was we brought back some of the old deep computer vision machinery back to the deep learning era from the deformable models. So these things were very, as I mentioned before, so very popular in the early 1990s, the active surface models, and has been long forgotten. So here what we proposed was, like, we reformulated them. We had to adapt them to work with measures with arbitrary degree and large vertex count. We reformulated to suit it to the context, to the modern context, and we integrated it with Voxel2Mesh, and we showed that we can better, so we can how we can integrate them and have better control on vertex deformations when we use Voxel2Mesh with active surface models. The title, you can have a look at the paper. It's titled Deep Active Surface Models. So now, after this, I go to a key issue with Voxel2Mesh that needs attention. So one of the issue is not one of the key. One is that this the memory issue, the vertex count issue that has with this mesh subdivision. So the thing is that we are competing with units and its variants. So these units are pretty good at exactly following the boundary information, like very accurately following the boundary. So to do this, we need to have, as I mentioned before, high number of vertices. So the thing is, increasing the vertex count has to be done in a much more intelligent way. At the moment, even the adaptive mesh unpooling is not good enough, in my opinion. We need to, it gives the edge in these cases. So in these cases, it gives the edge because the unit is making these crazy mistakes. Of course, if unit makes big mistakes in topology wise, false positive, so it has the edge. But if you look at the fine boundary, it can have sometimes little bit errors if you don't have enough vertex count, if you reduce the vertex count significantly. One could argue this vertex count is, this slight 1 or 2 pixel error at the boundary is not important. Yeah, I would agree, because when it come to modeling the overall shape, this couple of pixel error might be not that crucial, but still we have to improve it. It's something that has to be looked at and worked on. So the thing is that we worked on the models. When I did experiments, I worked on 32 GPUs with 32 gigabyte of memory. So I could increase vertex count way high and get good results. But what I noticed is that we can significantly reduce the vertex count and still have better accuracy if we have much better mesh subdivision strategies. So this is something that is open to everyone, is that to come up with good mesh subdivision strategies that would make it more practical, more to usable for everyone, that more commonplace. So this would increase. So if we can keep the vertex count lower, the training time would reduce, the memory consumption would reduce, and it would get more and more practical. Now the UNet has been fine-tuned by thousands of people, that it trains so fast, it consumes so less memory, and so the Voxel2Mesh, to compete with it, yeah, we have to improve these things. Yeah, but on a different note, you can argue, as I said before, this couple of pixel error is not important as well. But anyway, so this is one of the key issues I see with Voxel2Mesh at the moment. And the next thing, future directions. So the future directions I see mainly is the shape analysis. So this is what we need to move beyond, go into the future. So we have to go beyond segmentation. We have to look into further down the pipeline. So this is already done with CNNs. So if you look at, there are hundreds of papers that take X-ray images of the lung and say you have a COVID lung or not, or you have a cancer or a brain tumor in the MRI. But these things mainly works in the voxel domain, or this volumetric image settings, and they are primarily driven from texture features. Like this tumor is the texture is the inconsistency anomaly is visibly very so much with the texture. Of course, for a tumor you have a shape component as well, but there is a texture component along with it. And in my opinion, this texture component is very strong along with the shape component as well. But the texture plays a very strong part. For, let's say, you are detecting pneumonia on your lung, there is a very strong texture signal. The texture, it changes significantly. You are detecting cracks in a bone, texture is changing. But there are anomalies that arise due to shape anomalies, the differences in shape. Your liver is slightly large. There are too many ripples in the liver. This type of things, I don't see many papers in the literature. So this is something that people should, in my opinion, should look into. I mean, we have the machinery, we have the graph convolution networks and everything. People has to start, I mean, we can start working on these problems, that we take the measures and we try to analyze the shape of objects. Okay, this, of course, you can do the shape analysis in the voxel domain, but in my opinion, I don't think it's the efficient way. We should use measures for shape analysis, And even if you look at the past literature, people used measures for shape analysis. They did not use voxel representation for the shape analysis. And the most interesting thing is, like, even in 2020, there are papers that use PCA, principal component analysis, to do shape analysis. So there is room, like we can use deep learning techniques for doing shape analysis. And we are actually working on this problem at the moment as well. So this type of things. So the thing is, so now the Voxel2Mesh outputs the mesh, and these meshes can then be coupled with shape analysis techniques that would result in new biomarkers that could then use for screening and monitoring, and at the end, diagnosis or prognosis. So I put this orange arrows because down the line, these should also be replaced by deep learning models. But immediately now, what I see is we have the segmentation. Now it's time we can train large models that take input volume, produce output mesh, and then do the shape analysis. So this pipeline can be end-to-end trained with Voxel2Mesh architecture in producing the meshes. And I believe we can do exciting stuff with these things and make a good contribution for medical image analysis, from finding anomalies in shapes in organs, liver, heart, and so on. So that's what I see for the future. And so we have come to the end of my talk. And I think it's exactly 1 hour. So I think I did not overshoot too much.
Excellent. Thank you very much for the presentation. And I have some applause for you.
Thank you.
I hope you can hear that.
Yeah, I hear that.
So obviously our large audience would also applaud now, but we can't do that over Zoom because that causes synchronization problems. Yeah. So I'll just play it back.
That's nice.
So thank you. This was really a very nice presentation. I think you can stop sharing the screen.
Okay.
Then we see more of you.
Yes.
Excellent. I have a couple of questions here in the chat, and I would like to go through them step by step. So you already said that the main improvement that is published in this archive paper is concerning the initial placement of the input mesh. Can you elaborate a bit how critical that process is, and what they actually propose to make it better, or what additional ideas would be to make it more efficient?
So you mean by the archive paper this heart segmentation paper?
Exactly, but I guess you can also give us a couple of hints how to improve the initialization also directly with Voxel2Mesh, right? Yeah.
So here what they did was, like, in my case, there are two problems. So one is you have this binary segmentation problem. In that case, you start with single sphere and that's it. So that's the simple scenario. But then you have the heart, you have multi-class segmentation. You need the 4 initial. So in my experiments also, I had this synaptic junction, which I had in 3 colors: the presynaptic neuron, the postsynaptic neuron, and the synaptic junction, the 3. So in that case, what I had was, like, I had 3 spheres, but they were starting at the same location. And I had 3 different graph convolution layers for each part. So this was a little bit inefficient. So that means as the number of classes increase, the training times increase exponentially. So it was like it was not the most efficient way of putting things together. So what this guy said is, okay, we don't use different graph convolution layers for each class. We use the same weights, but we initialize the spheres at the correct place. So then the network is lighter, just like in the binary segmentation case. And because the thing with medical images is they are mostly registered already, like roughly registered. When a person is going to the MRI scan, you go in more or less the same direction, same position. So you have a rough idea about where the upper chamber is, the lower chamber is, and so and so. And it was not very clear to me how exactly they determine the position to place these spheres. There are a couple of ways you could do. You could either take the training data and compute the mean location of left ventricle, mean location of the right ventricle, and each the atriums as well. So you can have, once you have this mean location, you can place the spheres at these mean locations. Then the graph convolution layers would make it large or small at this corresponding portion. So that's one way that you could speed up. And the other thing is, like, instead of starting with a mesh or a sphere, you can start with Atlas. So then again, it's less deformation. The lesser the amount of deformation you have to make, faster the training, and more predictable the output, because unpredictable our outputs come when you make large deformations. Mm-hmm. So if you want to have, like, build more reliable systems, more systems that have more predictable outputs, you have to make sure your system is not making a lot of large deformation. So yes.
And if you compare that to classical methods like active shape models and so on, they all have a bounding box detector upfront that help placing the initial mesh. And
exactly.
I think this is something where your method is probably in the same ballpark, right?
Exactly. But the thing is, we can train the network sort of to find this initialization, so to get rid, because in the old days a human had to draw this bounding box, right, which was not the efficient way.
There's also bounding box detectors, but then again, you can also come up with considerable errors. And if you increase the capture range, then of course that would be very well appreciated to remove errors.
Yeah, of course. Yeah, I agree. So there is work to be done, but it's a direction that, because what I see in medical image segmentation at the moment is that there is so much attention paid towards just doing the segmentation, but not as much as attention paid to making a reliable prediction, quantifying uncertainty. Ideas like this is still, they are not out there. But if we are really want to build systems targeting real world, we have to address this problem. So these things has to be addressed. And the one when designing Voxel2Mesh, we had these things in mind, that we want to control our prediction. So, yeah.
Let me ask something else that is loosely related to the previous question. So if you have coarsely aligned volumes and then you apply Voxel2Mesh on different patients, I would argue that you also get at least a couple of correspondence points, the ones from the original sphere, that are shared among all the mesh representations that are created from your algorithm. Is that correct? Can you do you get aligned shapes by your algorithm?
Yeah, this is a good. So by correspondence point, do you mean key points, something like that?
Yeah, or semi-landmarks or something like that.
Landmarks, right? So this is something I'm still arguing in my head about. This idea of, because in the old literature, these landmarks are very popular, right? You are using landmarks to align stuff. You want to have the landmarks so that you can register the images, or you register the shape. Then you can do PC and all sort of things. But the thing is, you can, so if you take the hand or the face, you have landmarks. I have my tip of my nose, the eyes and stuff like that. But if you look at the liver or the hippocampus, I mean, I have to talk with a doctor first, but for me, I don't really see much landmarks. It's really difficult to define landmarks. So if we are going to develop shape analysis techniques, they has to not depend on landmarks. They should not rely on landmarks, in my opinion. That's my feel. Because even for the same person, the liver can be squashed or can change shape significantly depending on the shape he's. If he turned this side, it could have one shape, and he turned the other side, it could have one shape. And a thumb like this would be flattened on the another image. So the landmark idea, I'm not very familiar with this old literature, but I've not seen this landmark studies done for like organs like liver, heart, and stuff. I've seen for hand and face, but not for organs. Is there?
Yeah, this is why I was referring to semi-landmarks, because they don't need to be necessarily be related to an anatomical landmark, but some reproducible link between the meshes that allows to do statistics on them, such that you can use shape priors and stuff like that. Because I think that's very beautiful about your approach. If you have more or less roughly aligned input shapes, you should be able to do also shape statistics, at least on the coarsely resolved meshes. And then you're suddenly compatible with all active shape models and all of the classical methods in shape analysis. But on top, you have the beauty that you are much more flexible because you do the adaptive unpooling.
Yeah, exactly. So this is, so I think like we should bring ideas from this forgotten literature that people have forgotten. Because I mean, when you look at this stuff done in 1990, there are so many cool papers that has like.
You see, I'm starting to lose my hair, so I'm maybe one of the guys who still knows some of these papers.
Yes, exactly. So that's why. So there are nice mathematics developed on top of these things and then forgotten. And the thing is, like, we can bring them back and bring the deep learning machinery and combine them to do cool things. So this is yeah.
Exactly. So this is why I was very excited seeing your paper. First of all, it's a very cool paper, and the idea is just beautiful. And then I've immediately seen, there's this interesting links to the classical approaches that suddenly become feasible again. And I found that interesting. But there's, of course, also modern approaches like PointNet and so on, where you can also constrain global shapes that are obviously also appropriate, right?
You got muted.
Yes, I thought you wanted to reply.
Yeah. So what I wanted to say was like, so our previous work, like after the MICAI, our CUPR, the work was something like this. We took active surface models and we adapted it we linked it with Voxel2Mesh. And so it's basically we took all the machinery from the old days. We improved it. It needed some improvement. There were some things because in the old days the meshes were simple. They were like, it was not working for meshes with arbitrary degree vertices. So I had to improve how you compute surface derivatives and stuff like that. But after that, all the machinery is there from the active surface model, and I could just plug into the end of Voxel2Mesh and train the whole thing end to end. So it will appear on CUPR this year.
Oh, great! Is there a preprint already available?
Yes, it's already there. So that's a deep active surface model.
That's by the way, that would also be great if you share the links to the preprints that you already shown. Because
okay.
That would be
so
super
how can I do them?
We will post it in the description of the video, such that our audience can also access them. So
okay. So after the talk, when I will send you an email with all the links.
Absolutely. I will include it in the description such that people can see not just the Mikai paper, but all the very nice additions that you already put on top, which are also exciting to see. There is a question here. If you tried adaptive mesh unpooling like in an iterative manner or just once, it looks like you're only doing it once per stage, and whether you experienced it with several unpooling steps.
At the moment, I do once only per stage, but I have thought about trying it multiple times at a stage, but I have not yet. So it's the thing is, the reason I'm using adaptive unpooling is to control the number of vertices. And if I had multiple iteration at each iteration, it would be just adding more vertices and also removing. Of course, we can come up with a strategy. Yeah, I agree with this, because this strategy would make sense, because let's assume you have a very curvy region and you need more vertices there than a flat region. So if I do only one iteration at each stage, it would just add one vertex, and even with after 3 stages, it's not sufficient to represent this high frequency region. So if I can have more iteration of unpooling so that it adds more vertices to these high frequency regions and always remove these unnecessary vertices from the flat regions, so this would make sense, but I have not tried it.
Cool. There's another question here regarding sparse and multipath structures. This goes a bit into the direction of the hard model. Have you looked at vessel trees and like more compact meshes, sparse meshes?
Yeah, so I have to say this hard one is not our work. It's from a group from Berkeley. So it's So can you repeat the question?
How about vessel structures, vessel trees, and coronary arteries, or the brain?
Very nice question. So in our lab also we have a group of students that work with curvilinear structures. We have discussed this, but we are not still working on this idea. Is that we can use this to segment curvilinear structures on images, because one of the biggest challenges, as far as I have not done it directly with curvilinear structures, is like things go missing. Like you segment the curvilinear structures and like you have missing parts. So if you are deforming a curve to match the structure, it's more efficient. But the challenge is the topology of the structure is not known a priori. So for instance, for the liver, you can deform a sphere to this, but there is a workaround. So this workaround was proposed by Mesh RCNN. So there is it's an extension of Voxel2Mesh. You can call it an extension to Voxel2Mesh. Instead of using a sphere to initialize as the initialization, you use the output from the voxel decoder to initialize. So you have the voxel branch. So it would produce this occupancy grid representation of the object. You would run, they use Cubify. You can run Marching Cube or Cubify to convert this volumetric representation to a mesh. And once you have this mesh, you input this mesh to the mesh graph convolution layers to deform. But again, then comes the catch that since you are using the voxel decoder, there would be missing links, because the voxel decoder always breaks path. So it's a cat and mouse game that you will have to be clever to find the correct way to initialize the curvilinear structure. If you solve how to initialize, rest is straightforward. You find a way to initialize cleverly, how you can initialize for a given image. you don't know how the blood vessels are going. It can have 2 vessels, 3 vessels. Find a clever way to initialize the vessels, then the rest is you have Voxel2Mesh to take care of it.
Udaranga, thank you for all these presentation and also your nice answers to the questions. I think that summarizes your presentation very nicely. If you find a clever way of solving the problem, the rest is trivial. So I think that applies very well to your method.
I
do have another round of applause for you. I really enjoyed the presentation. So thank you very much.
Thank you very much for the invitation as well. Yes, thank you very much.
Thank you very much for accepting the invitation.
No problem. Yeah, my pleasure.
Yeah, you've seen we had a vivid discussion after the presentation. Really excellent research that he presented here. And I think that you might have 1 or 2 questions. So if you do have questions, don't hesitate to ask them either in the comments or send them by email or social media. And we would be very glad to forward them to Udaranga. So I hope you enjoyed this presentation as much as I did. And I'm very much looking forward to see you again in one of the next episodes of Beyond the Patterns. Thank you very much for watching, and bye-bye.